lesson 3 from Unit 1 on nonlinear functions. So this is a review of some of the main types of functions we're going to be seeing this year. I just want you to be able to, at the end of this lesson, sort of recognize the 4 types and know a few features about each of them, because they're going to be coming up throughout the course. You don't need to know a lot of details about each one, because that's more for pre-calculus, but I'll be letting you know what you need to know about the 4 types. So the first one you're probably most familiar with, polynomial functions. These are the most common type of functions we're going to see. So some features of these functions, I like to call them the bumpy functions because they just look like kind of like little roller coasters that go up and down and up and down and up and down. So they're written kind of like this. So like ax the power of n plus bx the power of n minus 1 plus dot dot dot. So they're always just like different powers of x. And the largest power is the degree of a polynomial. The domain, let me just give you an example. So f of x equals, like, let's say 4x cubed plus 5x minus 3. That would be a degree 3 polynomial. Okay. You could have a larger degree, like 5x to the power of 10 minus 13x squared plus 6 or something like that. That would be degree 10. Probably won't be seeing degree 10 polynomials, but you get the idea. So you can have any power. It's called a polynomial if it has that format. The domain is always, there's no square roots or fractions or anything like that. So it's just all real numbers. So you don't have to lift your pen when you draw these. There's always going to be arrows on the either side of the graph. It's smooth. Don't lift your pencil. The higher degree, the more bumps in the function. So larger degree, this is not a math term, the bumps, but E equals more bumps. Okay, so I'm going to show you what I mean now using Desmos. So we'll start with degree 2 polynomials. So you've studied these probably a lot in pre-calculus. So these are quadratic functions or parabolas. Okay, there's just one bump. Okay, and the numbers in front of x squared kind of determine whether it's facing up or down. Right, so yeah, it's just one bump. Degree 3 polynomials, though, they have 2 bumps. Let me just zoom out a little bit so you can see this whole graph. Okay, you can see the 2 bumps, and the numbers in front of x cubed and x squared kind of determine where those bumps lie. But usually there's 2 bumps there. And then if you had degree 4, you'd have 3 bumps. Degree 5 has 4 bumps, etc. There's lots of details to discuss in polynomials, and you do a whole unit on them in grade 12. The main thing I want you to be able to do is just recognize that something is a polynomial. Maybe find the zeros, understand the domain is all real numbers, and that's about it. Okay, so here's a function. Often too, it'll be written in a factored form. If the function's written in the factored form like this one, it's really easy to find the x-intercepts. So often, especially if you get into higher level math, if you're you always want to try and write it in the factored form, because then you can see the zeros right away. So the x-intercepts here are going to be x equals 1 and x equals -3. You can tell those just by looking at, so by looking at this, to make that 0, you would have to put in 1 into there. And so that's why x equals 1 with one of the zeros. And then by looking at the other factor, x plus 3, plugging -3 into that x position would give you 0, and 0 times anything is 0, so it would give you another 0. So on the graph, when we graph this, those points can be plotted right away, -3. Right on the 0. The y-intercept, you get that by plugging in f of 0. So 0 minus 1 squared, 0 plus 3. So you get 3. And what degree is this polynomial? So there's 2 factors of x minus 1 and 1 factor of x plus 3. So if you expanded all this out, the largest exponent would be a 3, because you would have 2x squared from expanding the first term and then another x. So this is degree 3. The function, I don't want you to worry about sketching these functions, really. I'm not going to test you on that. There's a whole section on curve sketching later in the course where we're going to be using calculus for this. I just want you to get, the idea is I want you to be able to recognize what type of function is by looking at the graph. I don't need you to be able to sketch the curve given the equation. So we're just going to do it in Desmos. So just going to erase what I've got here. So I'm going to type in f of x equals x minus 1 squared times, was it x plus 3? Yeah. So we can see it's that kind of bumpy looking function, right? 2 bumps because it's degree 3. So I'm just going to sketch this onto my curve. I'm not being accurate, okay? But anytime you see this sort of bumpy type function, it's going to be a polynomial. So it's going to look something like this. Okay, that's all you have to know. If it looks bumpy, it's got arrows going in both directions, it's going to be a polynomial. The domain and range, all real numbers. X is in R, Y is in R. Okay, this is the only time you get to sketch graphs this imprecisely in this course. I just want you to be able to recognize them. Okay, so that's polynomials, are bumpy functions defined for all values, the most common type of functions we're going to see. The next type of function we'll see a lot is radical functions. So these functions involve square roots. Couple points here. The domain is usually restricted. Because in a square root, you can't take the square root of a number. So the domain will be restricted because of that. And these functions are usually, unless they have some other extra term added on, they're usually only increasing or only decreasing. I'll show you what I mean by that. So these functions often start at a certain point because the domain is restricted on one side, and then they look like this. So they go up or they go like down like that. That's what the function usually looks like. So we're going to do an example. Here is a radical function, square root of x plus 5 minus 2. So we are going to sketch this function and find the intercepts. So the x-intercepts, so that is when the function is equal to 0. And because it's not factored or anything like the last one, you have to just solve for 0. So the 2 is going to go on the other side. And then you square both sides. You get 4, 5. Oh, sorry, the square root canceled out. Move the 5 over, you get x equals -1. So that is our 0, goes right there. Find the y-intercept. So that's going to be when you plug in x equals 0. So that's root 5 minus 2, which is going to be a decimal. I'll write the approximate number here. Approximately 0.236. So it's like about there. Before we get to the function, I'm just going to show you the domain. So the domain, we have to make sure that, remember this radicand, the part under the radical or the square root has to be positive. So if you just move the 5 to the other side, we have our domain. X is greater than or equal to -5. At -5, the y value is -2. So that's where our function begins, and then it just increases from there. I'm not going to sketch this super accurately. I'm just going to draw like that. Okay, so that's what that function looks like. I'll show you on decimals as well. X plus 5 of x equals square root. So if you're in decimals, you just type SQRT for square root. X plus 5 minus 2, and that's how it looks. Right, so if you see a function starts at a certain place and then increases from there or decreases from there, that's probably a radical function. The way you would get a decreasing one would be if you had a negative sign in front, and then it flips it, and then it's okay. So the main ideas for radical functions are they have a restricted domain, they're only ever increasing or decreasing, and that's pretty much it. The range we can get by looking at the graph, so we can see the y values are always greater than or equal to -2 for this graph. Okay. Good. So far we've done 2 types. Now we'll do a 3rd type, rational functions. We will see these a lot as well. You study these a little bit in Pre-Calculus 12. You go into details about asymptotes and holes in the graph. Here, I just want you to be able to recognize them and find the domains and restrictions. Okay, so the functions are of the form, so rational in math means fraction. If a number is rational, it can be written as a fraction. So a rational function is when you have a polynomial in the numerator and a polynomial in the denominator. P of x and q of x are polynomials. So like an example could be like x squared plus 5, that's a polynomial, over x minus 4. The domain is going to be usually restricted, but sometimes it depends on what q of x is. So remember, for a fraction, we cannot divide by 0. So if there's an x value that makes q of x equal to 0, that's where your domain is going to be restricted. Q of x cannot be equal to 0. And many rational functions have horizontal and or vertical asymptotes. So we're going to see that in the example down below. So an asymptote, remember, is a line that your function approaches but doesn't cross and gets closer and closer and closer to. So I don't expect you to be able to graph one of these. So that topic is covered in Pre-Calc 12, but you should recognize, looking at a function, you should be able to say, okay, yeah, that function is probably a rational function. And then you should be able to tell certain things about the function if you have its formula. So for example, let's say we had the equation 4 over x plus 2. Let's find the x-intercept. So that's where the function is equal to 0, x plus 2. This function cannot be equal to 0. Think about that for a second. Why can this function not be equal to 0? So for a fraction to equal 0, the numerator has to be 0. 0 divided by something is 0. Well, the numerator is 4. 4 divided by something cannot equal 0. So there are no x-intercepts. Y-intercept, that's where x equals 0. So let's plug that in and see what that is. That'll be 2, so I'll put that on my graph. Okay, vertical asymptotes. So the domain is going to give you the vertical asymptote here. So we'll get that after we sketch the graph. Let's do the domain first, and then we'll sketch the graph, and then we'll talk about the asymptotes. So the domain, that's where our denominator cannot be 0. So if you just move the 2 to the other side, that'll give you your restriction. In most cases, that will give you an asymptote at that point. Oops, not positive 2, negative 2. There we go. I'm going to draw a vertical line at that point. So I'm going to sketch the graph now. We'll use Desmos to do it. Again, you don't have to be able to sketch the graph. That's sort of what we're doing in Pre-Calc 12. Here, you just have to recognize that this is a rational function and look at some features. So notice here, we're going to have two asymptotes for this graph. The first one is the one we already mentioned at -2. Just going to make that a dotted line. I'm going to take away the grid lines too, so they're not in our way. Okay, so this is our graph so far. So notice the blue line approaches that -2, and it approaches it on this side too, but it never crosses. You have to lift your pencil to draw the other side of the graph. So that dotted line there at x equals -2 is a vertical asymptote. We also have an asymptote that's horizontal too, because look at the left side and the right side of this graph. The graph is approaching the x-axis but never crosses it. So y equals 0 is also an asymptote. I'll make it red and dotted too. So the graph approaches there. So this graph has a vertical and a horizontal asymptote. We're going to sketch it here. We don't have to be accurate. Just want you to get the idea and the shape. So if your graph has asymptotes, it's likely a rational function, especially, yeah, if it looks like this. Okay, so that's the graph of the function. Vertical asymptote is at x equals -2, and horizontal asymptote is at y equals 0. Okay, so rational functions. And last is exponential functions. So these have the form a to the power of x. There we go. So this time x is in the exponent. These functions increase very rapidly or decrease very rapidly. So the domain of these is always going to be all real numbers. You can always plug any number into an exponent. There's no restrictions on that. It could be 0, negative, or positive. And the range, unless something else is added on to it, is always going to be y is greater than, not equal to, but just greater than 0. You cannot make an exponent equal to 0. And there's always going to be a horizontal, h stands for horizontal, asymptote at y equals 0. Okay, so it's never going to reach y equals 0, but it will approach it. Okay, so let's just graph that using our Desmos, and then we'll answer the questions. Okay. So let's say we have y equals, or I'll use a different, yeah, I'll do a to the power of x. I had a defined up here. Let me just move it down here. And a is going to be from 0.1 to 4. Let's see what happens when I have different a values. I'm also going to put this as blue so we can see it a bit better. Okay. Okay, so right now a is 0.1. Notice the function is decreasing quite rapidly. As I change my a value, notice the shape of the graph changes a little bit. We're always decreasing, but it gets shallower. Okay, and then as that a value becomes greater than 1, now my graph is increasing. That's the same general shape, it's just going the other direction. Okay, less than 1, I'm decreasing. Greater than 1, I'm increasing. Less than 1, decreasing. Greater than 1, increasing. That's because if you have a decimal number less than 1, when you do an exponent with larger and larger x values, larger and larger exponents, the answer gets smaller and smaller. Okay. So if a is greater than 1, the base number is greater than 1, the function is increasing. If a is less than 1, the function is decreasing. Okay. So let's look at y equals 2 to the x. So in this case, a is 2, so this will be an increasing function. X-intercept 0. So we already said that this never hits the y-axis. The range is always greater than 0. So there's always going to be no zeros, because you cannot make a power equal to 0. But we'll have a y-intercept. So 2 to the power of 0 is equal to 1. So there's our y-intercept. Sketch the graph of the function. We can sketch this one out because it's not a lot of, again, some values here. And it's good to go over exponents. So I'll start with -3. I'll go to 4. Okay, so 2 to the power of -3. This is just a reminder. So a negative exponent means that you flip it to the denominator. And it's like you divide by 2 3 times. That's what the negative means. So it'd be 1/8. It's a very tiny number. It's really hard to graph. Try my best. It's kind of there. 2 to the power of -2. So it's 1/2 squared. So it'd be 1/4. Hard to graph, maybe there. 2 to the power of -1 would be 1/2. So that's about here. 2 to the power of 0 equals 1. 2 to the power of 1 equals 2. So there. 2 squared is 4, and now it's going to increase quite rapidly. 2 cubed is 8. So things that you would model with exponential functions would be like bacterial example. Bacteria grows very rapidly, very quickly, doubles every 20 minutes. So things like that you want to model like this, where they increase very fast, very quickly. Okay, so there's your graph. Okay, and because a is greater than 1, we have an increasing function here. So this is increasing, and the domain and range are always the same for all exponential functions. The domain is always all x values. There's no restrictions on the domain, and the range is y is greater than 0. So this does have a horizontal asymptote. It's always going to be in the same spot at y equals 0. So that's how you can tell it apart from the rational functions. So rational functions have asymptotes also, but they're going to be in different spots depending on what the equation is. And you can have vertical and horizontal. Whereas if you're trying to look at an exponential function, it's going to have an asymptote, but there's not going to be any restrictions on the domain, so no vertical asymptotes, and the horizontal one's always going to be at y equals 0. Okay, so that's it. I just want you to be able to know some of the features of those 4 types of functions. And if I gave you a graph and asked which of those 4 types is it, you should be able to answer. And then there's also some application questions in the assignment that will give you a feel for what kind of application questions I could ask as well. But I will always provide a graph. You don't have to draw the graph yourself. Okay, so I'm at the end of the lesson.